introduce Omri Ben-Eliezer from Tel Aviv University, who is now visiting here. And I know him quite some time, but I'll not tell you much about him. And he works in property testing, mostly for ordered structures. And today he will tell us about finding monotone patterns in sublinear time.
Thank you, Noga. So this is joint work with Clément Canon from Stanford, Shoam Letzter from ETH, and Eric Weingarten from Columbia University. So a classical problem in computer science asks, given a sequence, an array of numbers, to find the longest increasing subsequence. So what do I mean by that? I want to find k elements x1 up to xk so that the values are increasing. So where the number of elements is as large as possible. Now, one question that is interesting in this front is whether we can approximate the length of the longest increasing subsequence in sublinear time. And this is related to many other very interesting problems in strings. So for example, edit distance and other kinds of interesting distances. I will not talk about it here, but there's a lot of exciting recent advances on this kind of problems in strings. Okay, so actually there is an additive approximation for the longest increasing subsequence in sublinear time, actually in polylogarithmic time. This was shown by Zaks and Seshadri. But we don't know much more. Okay, so actually there are also some upcoming results that are related to the additive approximation case. But we don't know much about multiplicative approximation. So nothing is known about giving, for example, a two multiplicative approximation of the LAS length sublinearly. I mean, there are some results about that are sublinear space, but not sublinear time. Okay, so one way to try to attack that is from the perspective of property testing. Okay, and this talk will be about, we'll consider the longest increasing subsequence problem from the property testing perspective. So the property that we will test, I will give the exact definition in a moment, but the property that we will test is whether the LAS length of the sequence is at most some parameter k. Okay, so let's see the definition of the problem. We are given some array of real numbers. It doesn't have to be real numbers, just, let's say, an ordered set. That is, let's say, infinite, but we can also ask this problem in finite sets. But anyway, let's for simplicity say that the numbers are just real numbers. And we say that, given an array that is far from having a small LAS length, I want to find some proof for that. I want to find some increasing subsequence that is of length k. And this will prove that the LAS length is at least k. Okay, so I need to tell you what I mean by epsilon far in this case. So we say that the sequence is epsilon far from having this property if we need to change many entries in the sequence in order to satisfy the property. And in our case, so being far from having this property means more or less that we have many disjoint increasing subsequences of length k. So for example, in this drawing, you see 3 disjoint increasing subsequences. And by disjoint, I mean that no two of them share an element. Okay, so just to restate the problem, I think this is the more convenient point of view. So let's fix. Okay, so we will consider the case of that the sequence has short LAS. So we will fix the parameter that determines the LAS length. Okay, so let's fix k, and we are given an array of real numbers that contains many disjoint copies of increasing subsequences of this length k. And we need to find one of them. We need to find one such copy of an increasing subsequence. Now, the copy that we need to find doesn't have to be one of these original ones. So as you can see, this is outputting this increasing subsequence of length 3 is also a valid answer. Yes?
So can you go back to the one where you're characterizing this as disjoint sequences? Right. So here, don't we need epsilon n to be smaller than k?
Yes. So
epsilon n is larger than k. Let's say it's 2 times k. Then this equivalence sounds fishy.
Right. So this formulation is correct when k is fixed, and actually the problem that we actually consider is this one, and therefore the results that we'll get will be for fixed k. But it is very interesting to understand the structure of sequences that are far from having LAS lengths at most k when k is not constant. So yeah, so we will only use this point of view, which is only valid when k is fixed. And well, it is actually a very interesting open problem. I'll tell a bit about it later, about what's going on when k is not fixed.
So then I'm actually still missing something. So suppose k is fixed and constant. That's what you're saying.
Yes.
Let's say k is 10. Then isn't it? Like you can change those 10 entries and make it a strictly decreasing sequence. So it's not. It's possible that it's not far. Possible.
Yeah. So basically, what I okay. So on one hand, so one of the directions is trivial, and the other is not that difficult, but not trivial. So So if we have many disjoint increasing subsequences, then it's hard to be free from them, to have short LAS lengths. We need to modify elements in each of them. So
okay, right. So let me
that's yeah.
Maybe this might be clearer. So if f is epsilon far from free having LAS length k, doesn't it mean that it should at least have LAS of length epsilon n plus k?
It's
No.
epsilon far from not having an increasing sequence of size k.
Right. So if the LIS is epsilon n, at least for some of them, you could fix it so that there is nothing left.
Yeah, but it could be that
Yes.
LIS is
It could-
size
yeah.
k, and still you are far. You have many of them.
Yeah, it could be this case, but it's always the case that you have. I mean, it might be that you have a long one that decomposes into many disjoint length k ones. Okay, so we will just talk about this formulation. And okay, so monotonicity testing is the simplest spatial case, basically, of this problem. So, so the monotonicity testing problem asks to given an array to distinguish between the case that the array is monotone and the case that the array is far from monotone. But being monotone, for example, non-increasing, it doesn't really matter. But being monotone non-increasing means that we don't have a pair of elements that are increasing in some sense. So the LAS length is exactly 1. So it's equivalent to having LAS length less than 2. So this is basically the spatial case where k equals 2. Okay, and another way to view this property. So having short LAS lengths means So this is a special case of Dilworth's theorem in order theory. It means that the sequence is decomposable into a small number of non-increasing, of monotone non-increasing subsequences. Okay, so that was the problem. And now I want to tell a few words about the previous results, and then I'll tell you the results that I'll present today. So monotonicity testing is quite well investigated. So it's known that for this case there is, so if your algorithm, if the algorithm to find an increasing subsequence, in this case just to find a pair of elements where the second one is bigger than the first one. So for non-adaptive algorithms, it suffices to make O of log n queries to find such a pattern, and it's actually tight. And it's even tight actually for adaptive algorithms. And for general fixed K, there is a result by Neumann, Rabinovich, Rajendra Prasad, and Zoller that if K is fixed, then in fact there is an algorithm to find an increasing subsequence of length K in polylogarithmic time, so log n to the K squared, roughly. Now, let me mention again the result in the other end of the spectrum, where, when K is very large. So the testing problem in this case is a bit harder than additive approximation. So if we would have been able to solve the testing problem here, then we would get additive approximation. And again, there is an additive approximation algorithm that makes polylog queries. Okay, but nothing is known in the middle. So we know a bit in the fixed K regime and a bit in the linear regime, but we don't know anything in the middle. Okay, so our results will be in the fixed K regime. So our main result is that actually there is a non-adaptive algorithm that for any fixed K, and okay, so there is some dependence on epsilon, but let's assume epsilon is fixed. It makes roughly log n to the log K in base 2, the integral part of it, this number of queries. And in fact, this is tight, so it's actually, yeah, okay, so this should also be the integral part of it. So in fact, for any fixed K, the number of non-adaptive queries that are needed to find an increasing subsequence of length K is roughly log n to the log K. Okay, so any questions about the problem formulation, about any of the results?
So is there anything you get by combining the two upper bounds from before? Can you iterate? So since it's not on the previous slide, since this is non-adaptive, can you sample a few and then apply the second one?
So which one? So to get this O of log n? Yes. No, you can't use that. I mean, you can't use the K squared one as is. I mean, to get anything.
So you think of K squared as much less than log n, right?
Yeah. Yeah. So we fix K in general.
So I'm guessing C epsilon K is like horrible in K. That's why it doesn't.
It's
go
exponential in K, yes. And actually, if
you get something in it for like very small.
Yes, right.
That's adaptive.
But then okay. But then we actually. Yeah. Okay. But we consider. Okay. So I'll have to think about it. But we consider the problem where we have. We implicitly assume somewhere that K is fixed. So in this formulation. But yeah, it might imply something. So okay. Yes, but I think if we would be able to improve this dependence on k to something maybe polynomial, then it would give hope that maybe we can get much better algorithms that work for much better k. Maybe we will have to revisit the formulation of the reformulation of the problem, but it would give some hope. So this is actually a good question and good possible problem for future research.
Okay, that'll be your entire PhD, right?
Okay, so just to get a sense of why there is some dependence in N, so just a few words about a non-adaptive lower bound for monotonicity testing for the case k equals 2. So here you can see different types of constructions of sequences that are far from monotone, far from 1 to 3. So to answer your question, none of these, well, most of these don't have long increasing subsequences. I think none of these even has that. And it's not hard to show that in some sense queries that help to capture the construction in type 1 do not help in other types at all. And it's actually true for any pair of types.
So what is type?
So the construction of type I, so you decompose into like windows of lengths that are 2 to the I, or maybe 2 to the I plus 1. And then to find a copy, you must query a pair of elements in this window size, basically.
To find a what?
So if you want to find a 1-2 copy, an increasing sequence of length 2, then you have to query a pair of elements that the distance between them will be like roughly 2 to the I. Yes, and it just wouldn't help in other types. Okay, so now let's see a basic paradigm for such an algorithm. This will give the log n to the k-squared algorithm. So let's say our array contains many disjoint 1-2 copies, and we say that the width of a pair of elements is the log of the distance between them. Okay, so if you look at a window of size 2 to the w roughly, to the w plus 1 maybe, and you look at so typically the copies that you will see, you put a separator in the middle of this window, then typically the copies that will be separated by this separator, by this line, will be of width w. This is what it means. Okay, so if we have many disjoint 1-2 copies, so each of them has a width. So there is some widths, not too many widths, only log n of them, so roughly. So there is some width that contains many copies with this width. Okay, and if we look at a window of this size, and we look at all the copies where the one entry, the smaller entry, is to the left of the separator, and the 2 entries to the right of the separator. And now we just split these copies. Okay, so we take the median of the ones. We take this dashed line that is the median value of the 1 values. Then if we take any 1 value that is below it, and any 2 value, any red element that corresponds to a 1 value above the median, then each of them is a 1-2 copy. So if we find each of them, it suffices for us to win. Okay, now so a simple algorithm that can use this fact is to just okay, so if we take W to be this width where we have many copies, then typically, if we look at a window of this width, with pretty good probability, with probability at least 1 over log n, asymptotically, this window will actually contain many disjoint 1-2 copies, and then it will suffice to just okay, so we don't know what is this good width, so we'll just enumerate over all widths, and for each of them we'll take sufficiently many windows, and in each window we'll query sufficiently many elements. And okay, so the query complexity will be log cubed in this case, and in fact it can be okay. So you can just iterate this argument when you have larger k, and the query complexity will be log n to the k squared. And it can be, well, if we do some binning, then it can be improved to log n to the O of k, but no better than that. So we need something else if we want to improve on that. Okay, so how can we devise a more efficient paradigm? So let's try to take a bit of a more careful analysis of what is going on, and let's see where we are stuck. So okay, so again we consider the case. Okay, so let's consider the simplest case, the case of monotonicity testing that corresponds to k equals 2. And okay, now let's look at a pair of elements that have widths w. So the distance between them is roughly 2 to the w. So and we say now that another element L cuts this pair with slack if it's between them, but quite far from x and quite far from y. So it has to be at least x plus some small constant times roughly the distance between them, and at most y minus this same expression. So if you look at it visually, it's something like this. Okay, so this is a very simple claim. So the total number of elements that cut this pair with slack, basically all elements that are between these two dashed lines, is linear in the distance between them. Okay. Now I want to take the dual view. So I want to look at such an L, such a middle element, and see which pairs it cuts with slack. Okay. So if we look at let's say we consider L as the middle, and we look at a window of width of length 2 to the w around it, roughly. So the density of 1-2 copies around this middle point is probably what you might expect it to be. So it's the number of elements in our collection of 1-2 copies that have width w, and that are also cut by L with slack. So L is roughly in the middle with respect to these copies. And okay, so it's a density. It's we divide it by the roughly the total number of possible copies that we can have of this form.
So the number of copies is not 2 to the 2w, because you can choose the 1 and you can choose the 2.
Why 2 to the 2w? So
you choose pairs, or you look only at the disjoint.
Yeah, I look at disjoint.
Not at all of them, but just
yes. So a collection is of disjoint copies. Right. We just consider this right now. Okay, so this is what densities look like. So density is roughly if you take the window of width w, it's roughly and you pick a random element. It's roughly the probability that this element will be contained in some copy. Okay. So this is how densities should be thought of. Okay, and now Okay, so now we know that our array is far from being 1, 2, 3. It's far from monotone. So it contains many disjoint copies of 1, 2. And I want to claim, so it's also a very simple claim, that that if you take an L, you take a middle point, and you look at the sum of densities in all possible widths around it, then the expected sum will be quite big. It will be at least, so if we think of epsilon as a constant, it will be typically at least a constant. It will be expectedly at least a constant. Okay, so yeah, so why it's the case? It's basically double counting. So so this the expectation. Okay, so we want to show that the sum over all possible L of the sum in the expectation is at least is roughly epsilon n. So instead of counting from this direction, we count it from the other direction. So for any pair, so we know that we have epsilon n disjoint 1, 2 copies. So for each such copy, we've seen before that there are many elements that cut it with slack. So there are roughly 2 to the w elements that cut it with slack if the width is w. But since we divide by 2 to the w, then we get what we wanted. We get that the sum is linear in theta in epsilon times n. Okay, so this is basically the proof. Now, okay, so we know that expectedly this sum is linear in epsilon. Okay, so let's fix one L and see what happens if this L is at least linear in epsilon. The sum is at least linear in epsilon. So okay, let's say we know this for some specific L, and okay, so I propose now an algorithm to find a 1, 2 copy, and the algorithm will be quite simple. So for any possible widths, we will query sufficiently many uniform elements in the window of length 2 to the w. Okay. So yeah, so the reason that this will work, the reason that this will find a 1, 2 copy, is that in width w, so the probability that we will so the probability that we will find a copy is roughly this density over epsilon. If we sum over all w, then we get this. Okay, but this only works if okay, so yeah, so and from this we can devise an algorithm that just okay. So if this condition holds for many possible values of L, then we can just consider the following algorithm to find the 1, 2 copy. So pick sufficiently many candidates for the value of L, and for each such candidate, to run the algorithm from the previous slide. Okay, but this will only work if this sum, the sum of densities, is large for many values of L. Okay, so we know that the expected sum is at least linear in epsilon, but it might be the case that there are a few values of L where this sum is very large, and for other values of L, this sum might even be 0. So okay, so how can we deal with it? Okay, so now what I want to show now is actually a very simple and very seemingly naive way of to restructure the 1, 2 copies in a way that will just solve this problem, that it will just eliminate it. Okay, so and in fact we will it will give us some another type of another possible algorithm to query elements that will find increasing subsequences of a different form. Okay, so so how does the greedy restructuring algorithm looks like? So basically we sweep from left to right, and we look for 1 entries of copies. Okay, so let's see. And instead of, okay, so this gray element is matched to the other gray element right now, but instead we want to match it to the first element among those that participate in copies that can be matched to it. So for this element, the first element that can be matched to it is this one, because it's bigger than it and it's after it. So this is also a valid one to copy.
What about the y?
Yeah, so actually we could also use this one, but yeah, it's so my algorithm doesn't use it, but we could.
So what is the color coding? What's white here and what's black?
Yeah, so each pair of elements of the same color are paired in the original collection of copies.
And whites are where?
Yeah, so these two are copy. Maybe it's hard to see that.
4 whites. Okay, they're not actually whites.
Yeah, they're off whites, I guess.
Okay.
Okay, yeah, and now, okay, so this is what we will do. It's a very simple, greedy restructuring procedure.
So you take it only among the elements that participated in the disjoint, in the collection of disjoint pairs. That's why you didn't take the white one, or?
Yeah, so I just used okay, so it's not, it doesn't really matter, but let's, for our purpose, let's just use, it doesn't, but we just, let's say we just look at elements that participate in original copies. Okay, now, okay, so for the next element, so there is, okay, so the green one fits as a, fits in order to close a pair. And we can continue and so on. Okay, and so this is so this is the collection of new copies that we have. And okay, so what's so good about it? It's not clear what we did here. So okay, so first this collection is roughly the same size for our purposes as the original collection. So each pair that we inserted to the new collection destroys at most 2 pairs from the original collection in some sense. So they are roughly of the same size, but the magical property that will actually solve our problems is that, well, it doesn't look magical, but we'll see why it's so beneficial. So if, okay, so let's say that we have a pair of elements, x and x prime. We know that x comes before x prime. So that's this gray guy. And if we know that the value that is, and if we know that the element that is matched to x comes after the element that is matched to x prime, then we also know something about the values, about the, so we know that the value of this element is also bigger than the value of the element matched to x prime. And why is that? So let's look at what happens when our sweep sees x. So at this point, none of these elements is matched, but still the sweep decided to, so the algorithm decided to match y to x and not y prime. So y prime, the value of y prime comes before y, but it was not matched to x. So it must be the case that the value of y prime is no bigger than the value of x. On the other hand, the value of y is bigger than the value of x. So this is what we get. Okay, and so yeah, so we had this problem that that it might be the case that there is a large variation in the value of this sum, of the sum of densities. Okay, so let's see how this magical claim helps clean down things a bit. Okay, so let's look at an element at a potential middle point L, and let's look at all of the pairs, all of the 1-2 copies that it cuts with slack. So since cutting with slack means that it basically lies somewhere in the middle of the copy, and since we know that the first element in this, okay, so since the conditions of this claim hold, so okay, so I didn't mention that, but we look now at the restructured collection of copies. So in this collection, since we know that, for example, for these twos of copies, so the ones are somewhere here, and these twos are the ones are somewhere here. So we know that the ones are further to the left, and still they were matched to elements here. So now the conditions of the claim hold, and we have a structure that looks roughly like this. So we know that twos that come from pairs that have smaller widths typically have smaller value. Oops. Okay, so and our idea will be that in this case, okay, so if each of these specific densities is quite small, but the sum of them is large enough, then we can employ a different strategy that will find increasing subsequences of a different structure. Okay, so let's see. So the claim is that if all of the single densities are bounded by some small parameter alpha, and the sum of all densities is much bigger than that, then the right algorithm, so then a good algorithm for this case, is to just sample sufficiently many elements in each of the windows of so we pick a number of elements that depends only on the large element, on beta, on the large parameter, on beta, from each of these windows. If we employ sampling of this type, then this will find actually an increasing subsequence. Okay, so why is it the case? So basically, the total number of sampled elements, of elements that we will capture in this case, will actually, it's not hard to show that it actually depends only on beta. It doesn't depend on alpha. So the total so the total number of elements that will be sampled will be large enough if we make a number of queries that is roughly 1 over beta in every width. But okay, so this we know regardless of alpha. But additionally, if alpha is small, then typically we'll not sample many elements from the same when looking at window of the same width. So typically they will come from k different widths. But now if we have an element from this width and an element from this one and an element from this one, then these three already constitute an increasing subsequence. So just take one from each width. Okay, so this is basically this simple claim is and the structural observation that the fact that the restructuring of the copies revealed this kind of structure is basically the most important part of the proof, even for general case. So right now we just look at the case where of monotonicity testing. We just look at the increasing subsequences of length 2. But this is kind of the the observation and claim that solves it all. The rest is just technicalities. Well, they're not trivial technicalities, but this is basically what gives the good algorithm. So, okay, so if there's one message that I want to say, that I want to this talk to give is that sometimes this kind of greedy, simple greedy methods can just completely solve your problem. So they can sometimes reveal interesting structure that you wouldn't expect them to. Okay, now just to say a few words why we can use the growing suffixes for monotonicity testing. So let's say we have a collection of many disjoint 1-2 copies. Let's say it's the restructured collection. So, and what we roughly want to do is either to, okay, so we want to, our problem our original problem was that we could have had some, okay, so we know that, let's return to the, yeah, so what we know is that the expected value of the sum of densities is quite big, but our problem was in the case where there's lots of variance in this. So there are only a few L's that contribute a lot to this expectation, but most of the L's, this sum is small. So let's see how to solve this. Okay, so basically, as long as we have some candidates for growing suffixes, we'll remove pairs in some sense. So as long as we have a middle point for which the sum of densities, so this is the beta, the large parameter, is much bigger than the maximum of the densities. So this is the alpha, basically. So we just remove some pair that contributes to the fact that L is a growing that L starts a growing suffix in some sense. And each time it can be shown that in fact each time you remove a pair from the collection, the first element of this pair is a start of a growing suffix. So growing suffix is this kind of structure. Okay, now in the end of the process, either we removed many pairs from the collection, and each time we removed a pair from the collection, we added it as a start of a growing suffix. So either we have many points that start a growing suffix, or we didn't remove many pairs from the collection. And in this case, we have still a large collection of pairs, and also the sum of densities for each point, for each middle point, is not too large. So we don't have this variance problem. Okay, so the second case we already solved in the beginning, and for the first case we ran the growing suffixes algorithm. So this was basically it's certainly not the simplest proof for monotonicity testing. There are some cleaner proofs for this special case, but in fact this kind of proof will generalize to the case of general K, of general fixed K. Okay, so any questions? I think it's a good point for questions.
Is there any abstract nonsense that buys you something, like VC dimension?
I don't think so.
I mean, let's say there was a prior distribution on the inputs, which you can almost assume without loss of generality. If you ask the most informative query, are there examples where there is no progress measure that you can define?
I'm not sure. It's a good question.
How do you generalize your types to general K?
Oh, we'll see it in the end, but basically it's an iterated construction. So that's you're talking about the lower bound now.
Okay. No, I'm still talking about the upper bound because you said.
So for upper bound, you can't say there are types. I mean, you need to solve. You need to. So for the lower bounds, we've seen that there are different types of sequences that are far from monotone. And to capture a one-to copy in each of them, you need different queries. So talking about types is restricted to the lower bound side.
The question was here. Here's a type of pair was the width was 2 to the w, and now you will have the type of a k tuple.
Yes. So yeah, we will get to it soon. So it's but it's kind of okay. Yeah. So let's see how. Okay, so just one final word about the case where k equals 2, about the monotonicity testing case. So, in fact, what we call the second case, which was the case where the densities behaved well. So, in fact, we get a stronger condition. So, there are many values of L for which there is a single density that is large. It's not that just that the sum of densities is large, but there is a single density that is large. So, for example, this L2, if you look at this specific width around it, then the density of copies with this width cut by L2 will be large. And this will be very useful. Okay. And now, okay, so just, so the general case is just basically, okay, if you take this proof for monotonicity and kind of iterate it, this will give the proof for the general case, the algorithm for the general case. So, okay, so there are some, so the definitions are generalized in relatively natural way. So, okay, so one thing that's important to say is that the growing suffixes algorithm actually finds long increasing subsequences. It's quite easy to find the increasing subsequences that are much longer than what we actually need. So we more or less need to address the other case, the case where the densities are well behaved. And for this, we'll just iterate the splittable intervals method, which is this one. Okay, so yeah, so again, let's suppose that the array contains many disjoint increasing subsequences of length k, and we employ the greedy rematching. It's kind of the same, but you do it an element by element. But you get similar guarantees, and you get the same magical claim that will allow us to use growing suffixes. And here to cut something with slack means that we basically we look at the full profile of widths of a copy, and we look at the pair of elements in this copy that are furthest away, and cutting the copy with slack means that we cut this pair with slack, basically. Okay, so densities are defined similarly, and well, basically all the definitions are essentially the same. And okay, and what I want to use is basically to iterate the reasoning for the splittable intervals kind of reasoning. Okay, so let's see what it gives. So you kind of look at structures like this. Oops. So we can define such a structure by 3 descriptors. So this is kind of the structure that we look at. So for example, this kind of okay. So this was created by taking an element, some L, and looking at that has, for some certain density, it has, for some certain width, it has high density with respect to this width. So looking at this this kind of interval. So this is, for example, one such type of an interval. And then you continue in the left side of it and in the right side of it. So we know that there's a large density of sub-copies in this side and a large density of sub-copies that complement them in this side. So you can continue this recursively. And now the way to, okay, so how can we use these for an algorithm? So basically what we want to do is, okay, let's maybe see it visually, but the idea is you just pick a relatively small number of elements as the base layer for our algorithm, and then for each and then for sufficiently many times, which is basically the depth of it's not exactly the depth of the tree, but it's for a log of number of the leaves of the tree. So this tree, it has each leaf corresponds to an element. Okay, so if we're looking for increasing subsequences of length k, then we have k leaves in this tree. And okay, so if we iterate roughly log of this number of iterations, and for each element that we currently have, so we started with a small number of elements, and for each element that we currently have, we just query elements at all possible widths around it. Then this will help us in finding copies. Okay, let's see why. I think the visual example gives that. So suppose that we're fortunate to find some entry that is the 2 entry of some copy. And now, so this happened, for example, in the first. This happened in the first iteration where you picked a small amount of elements. And now, what I want to do is query uniform elements at all possible widths. So if we are lucky, we know that in this interval, so we have a large density of copies. So if we are lucky, we will be able to find some one entry of a copy that will match to this 2 entry. And also, we know that this interval is quite dense. So if we are lucky, we will also find some element that corresponds to a 3 entry of a copy from this in this width. But it's not. We can't hope that at this point, for example, to query both an element from here and from here because the number of elements that we query, the number of elements that is a constant. Well, depends just on epsilon. And it doesn't depend on the width. So the density of the elements that we actually will sample here is quite small. So it will be hard to find some structures with a high granularity. But this is the reason we apply this iterated algorithm. So if we manage to sample this element, then in the next iteration we'll look at all possible widths, and if we are lucky, we will find this one as well. Okay, so this is more or less the reason why the answer for this the non-adaptive query complexity and also the running time for finding an increasing length k subsequence is log n to the log k. So basically, you can if you take the tree view, then each iteration is, you can look at it as starting from some leaf and going up to the root because you query in all possible widths. And this decomposes the tree to a tree that okay, so and then when you run the algorithm iteratively, you run it on trees that are much smaller than the original one. So this is the kind of the reasoning that the answer is log n to the log k. Okay, so basically that's it about the algorithm, about the upper bound. And just to say one word maybe about the lower bound, we looked at this lower bound for monotonicity testing before. So the general lower bound is kind of an iterated construction of the monotonicity testing non-adaptive lower bound. And okay, so here you need to define types of constructions in a way that is much more delicate, and but it still can be done. Okay, so at the most basic level, the reasoning is still the same, and the reasoning is that a certain number of queries cannot capture that many types. Okay, so that's basically it about the results. I just want to mention some.
The definition of type now will have to do with all the differences between consecutive.
Yeah, so it's a much more complicated type. So it's kind of a tree structure that each type corresponds to a tree structure that is somewhat related to the tree structures from the upper bound. So basically, so you have log k layers to the construction, and each layer you can choose widths in many possible types. So the widths are roughly of log n types, and the queries that help. Okay, so this is not accurate, but it's roughly accurate. That queries that help for a certain type for a certain type of iterated construction don't help for other types of iterated constructions.
So it seems that this works for every k.
It should, yes. But it only gives something that is, okay, so the epsilon is just, it has to be at most 1 over k. So it wouldn't work for constant epsilon if k is large.
Why? So what's the dependence of
It's, okay, so in this construction, epsilon is exactly 1 over k, actually. And yeah, I don't know how to construct examples for larger k.
And do we have good algorithms if we are allowing sub-constant error? Can we beat your algorithm?
So for
So
general k, the question is about general k?
If k is constant, then it's sub-constant.
Okay, so this is, okay, so yeah, so this is an optimal non-adaptive algorithm, and so it's natural to ask whether there are better adaptive algorithms for this, for constant k. And okay, and this is actually a work in progress. And we believe the answer is yes. We believe that adaptivity can help here. And yeah, okay, so actually these two open questions answer the. So we believe, so it's still a work in progress, but we believe the answer is log n. So it's in the adaptive case, for any fixed k, finding an increasing subsequence of length k is as hard, basically, as just monotonicity testing, as the simplest case, which is k equals 2. So I would bet on it, but I'm not sure that, yeah. But I'm not 100% sure that this is the answer.
Do you have a log n lower bound for adaptive algorithms?
Yes, the log n lower bound for monotonicity testing, which is also, there's also an adaptive lower bound, also carries on to this case. So
like log n times 2 to the O of k, or?
Yeah, so the dependence in k, it's still, we don't know how to nail it at this point, but yeah, I wouldn't be surprised if the right dependence would be polynomial, but this kind of reasoning still, I mean, maybe if we apply enough force, then we can get something. But what I told you today has an exponential dependence on k. And even in the adaptive case, we still don't know how to improve dependence on k, the constant that depends on k. Now, okay, but still, okay. So all of this talk was about the case where k is a constant, and still the big question of whether the LAS lengths can be approximated to a multiplicative constant factor by a sublinear algorithm. So we're not close to understanding it. I mean, both us and the groups that attack, I think, from as far as I know, the groups that attack this question from the other side, from the side where k is linear in n or close to it, we are still far from getting something that will apply across the whole range. So I think this is maybe the central open question that lies behind all of this kind of problems, at least for the LAS. Yes.
This is probably a good question, but for k really small, achieving a constant factor, is there any hope you could do anything sublinear? I mean, if your sequence is decreasing with one potential flip hidden in the entire sequence, you have to see the entire sequence, right? So to distinguish between 1 and 2.
Well, monotonicity testing distinguishes between 1 and 2. Actually, okay, so.
No, but it's in the property testing regime.
Okay.
It's assuming a distance.
Yeah.
That will never give you an multiple.
Yeah, without a kind of property testing assumptions, I don't think we can. I mean,
right.
Yeah.
So asking the question with the property testing assumption.
Yeah, that's right. Okay, so just to say it again, so the additive approximation algorithm doesn't assume anything. But if you want to get a multiplicative approximation, then you need to assume, you need some kind of, to distinguish between the case where the LAS length is at most k or far from at most k, or if you want a multiplicative approximation, far from at most 2k or something like this. You can't just, you need some kind of property testing assumption. Okay, and more generally, so this problem is also a special case of another kind of problem, of kind of pattern matching problems in the sublinear regime, which is also, here we also have many interesting open questions that we don't understand. So the general problem is, let's say we have an array that is far from not containing some pattern. It doesn't have to be a monotone pattern. So for example, this is the pattern 1, 3, 2. So the middle element is the largest and the leftmost element is smallest. And we need to find one such copy. So our problem is just this problem when the pattern is monotone. And here, so for non-adaptive algorithms, we understand them pretty well. We don't understand them completely, but we have very strong lower bounds for the non-adaptive case. Actually, it's interesting. So monotone patterns, as we've seen in this talk, you just need a polylogarithmic number of queries, but any other pattern, you need at least square root of n queries. And in fact, for most patterns of length k, you actually can just barely beat the union bound argument if you use non-adaptive algorithms. So they are very ineffective in this case. But we know almost nothing about the adaptive case. So there is, okay, so the pattern 1, 3, 2 can be found using an adaptive algorithm with polylogarithmic number of queries, but basically that's it. Basically that's what we know. So I think a very interesting open question in this front is whether for any constant length pattern, whether there is a polylogarithmic time algorithm to find it. Okay, so I think I'll finish here. Thank you.